tangent of v. Down below, this whole first term reduced to 1. Sine u over cosine u, tangent of u. Sine v over cosine v, tangent of v. And now we've derived the addition formula for tangent. Now again, do we want to go through all this writing to get the subtraction formula for tangent? Nah. And we don't have to. We can use negative angle identities. Again, if you go back to your negative angle identities, cosines of opposite angles were the same. Sines of opposite angles were opposites. Tangent is the same as sine over cosine. If you think about those things and put them together, then tangent of opposite angles are opposites. So, to get the last addition subtraction formula, what might we do? Well, we can take tangent of u minus v and think of it simply as tangent of u plus a negative v. Wow. Beautiful stuff. So, using our identity down here, that's equivalent to tangent of u plus tangent of negative v over 1 minus tangent of u times tangent of negative v. And now using our negative angle identities, the negative sign goes out front, so I get tangent of u minus tangent of v, since tangent of opposite angles are opposites. And down below, the negative sign here, using the negative angle identity, converts this sign into a positive. And I derive my last addition subtraction formula. So beautiful stuff. What have I done so far? Well, we've derived 6 cofunction formulas. We actually derived 3, and I just kind of showed you where they would go, how the other 3 could basically be derived from them using reciprocal identities. And then I derived all 6 of the addition subtraction formulas. Each one was kind of a buy one, get one free. We had to do a lot of work to get the first one, and then the second one was a consequence of the first by using negative angle identities. So the question that you're asking yourself is, when are we ever going to use this stuff? Well, let me show you a little bit, a couple different things that we're going to do here with these. Up till now, the only angles that we know the exact values for are special angles on a unit circle. Special angles on a unit circle. Pi over 6, pi over 4, pi over 3. So, well, suppose I wanted to know sine of pi over 12. And you're going, well, that's not a common angle from the unit circle. I have to use my calculator. Well, I'm out in the middle of the Sierra Nevada mountains. I don't have a calculator. The only way to do my triangulation and stuff to find my way back to civilization is to come up with sine of pi over 12. My life depends on it. I'm going to be disoriented until I find this sine value. And now that you've got the addition subtraction formulas, you think, wait. I know. I can think of pi over 12 as the difference of 2 common angles from the unit circle. And being the bright math students that you are, you say, oh yes, I can think of this as pi over 3 minus pi over 4. Look at that, because this is 4 pi over 12 minus 3 pi over 12. And 4 pi over 12 minus 3 pi over 12 equals what? Pi over 12. So then the sine of this angle must be the same as the sine of that. Well, now, this is like easy. I take this and write it as sine of the first angle, pi over 3, cosine of the second angle, pi over 4, minus cosine of the first angle, pi over 3, times sine of the second angle, pi over 4. Oh, wait. Yes, I'm recording myself on video teaching a lesson right now in room 205. I'm up in Goupil 205 if you're here. Yes? I don't. Nope. Okay. Okay, see you. Bye. So, little diversion there. All the more real, right? We're used to the phone ringing in the middle of class. Sine of pi over 3. Well, if you're confused, go back and draw a picture. That gives me root 3 over 2. Cosine of pi over 4. Root 2 over 2. Cosine of pi over 3. 1/2. Sine of pi over 2. Root 2 over 2. And so we get root 6 minus root 2 over 4. What a beautiful thing. That's the sine of pi over 12. Great stuff. So we can use these angles, these identities, to find the sines and other trig values for other angles. But that in and of itself, in the modern era, what's the point? All I got to do is put it in my calculator, hit sine pi over 12, presto, bam, out pops a button. Well, guess what, guys? This is used in calculus. Well, I know you're saying calculus. Well, that's why it's called pre-calculus. So we can learn get all the tools we need to actually do calculus. Because if you go back, let me erase the board here. If you go back to a little earlier in the year, we did something called the difference quotient. F of x plus h minus f of x over h. I gave you an interpretation of that with the little symbol, the limit as h goes to 0, to describe, if I were to draw a graph like this, here's a point x, and then here's a distance h, so this is x plus h. And then these are two values. So here's x, or x plus h, f of x plus h, and here's x, f of x. And then if I connect these two, this line segment connecting these 2 points has a slope attached to it, which is the change in y, f of x plus h minus f of x, over the change in x, which is h. Well, the idea in calculus is that we slide these points closer and closer and closer together until they're so close that they basically coincide. And at that point, the slope here of this curve is equal to the slope of the tangent to the curve. So then the question becomes, suppose my function was a sine wave, sine x. How could I find the derivative of sine x? Well, if I plug it into the difference quotient, and I'm going to not deal with the limit right now as h goes to 0, I would get sine of x plus h minus sine x over h. Well, what does that look like, guys? That's an addition formula. So in calculus, not now, I'm just giving you an honors bonus. This is, what's coming down the road next year. In fact, there are a couple exercises in Swakowski where you can get an opportunity to algebraically manipulate these. You could expand this into sine x cosine h plus cosine x sine h minus sine x over h. And you can do some regrouping. There's some calculus stuff that you don't know yet. But you can get it down into a form. And when you simplify everything, if you were to go through and do the whole thing and as h goes to 0, you would eventually come down. Next year in calculus, you'll derive or find out that the derivative of sine x is actually cosine x. Fun stuff. Fun stuff. So let's take a look. At the kind of learning opportunities that Swakowski is going to allow you to do, and that I'm going to allow you to do. This being our favorite section of the book, favorite chapter. Again, if you look over on the exercise on page 490, 491, they give you a whole series of terms, or of exercises. So let's quickly go through and do a couple of these.